Hey, Kenny, what's this I hear about the coriolis effect?
So the coriolis effect involves objects that are rotating. And the Earth is certainly an object that's rotating. In fact, it's about approximately a sphere that's rotating.
Oh, okay, so this means like in terms of weather and climate, that air masses, as they travel around the Earth, are going to be affected by this coriolis.
Right. So before we get involved too heavily with the coriolis effect, let's write down our old friend, the rate equation.
Okay.
Because we're definitely going to need this here. So rate is distance over time.
Right. And we have two circles here, or like flattened spheres, and we notice that they're identical except for these arrows. So what are these arrows?
So these arrows are perspective, actually. They deal with perspective. So if you're looking at the Earth from a certain perspective.
Okay, so let's say like down on the Earth.
Exactly. So if you're looking down upon the North Pole, the Earth appears to be moving in a counterclockwise direction.
Okay, so something like this.
However, if you change your perspective and now you're looking up at the South Pole, the Earth appears to be moving in a clockwise direction.
Ah, okay. So these two circles are basically like flattened spheres. We're looking either up or down upon the Earth.
Exactly.
And in this case, the arrows are moving what looks like counterclockwise.
Right. So the circle on my side is a view at the North Pole.
Okay. So mine's the opposite. Mine looks like it's moving clockwise. I must be looking up upon the South Pole.
Right.
Okay. So we have our two perspectives here. So let's talk about what happens to these air masses.
Okay, so let's say we have an air mass that's near the pole and near the North Pole, in fact.
Okay, and I'm going to do the same thing here on my South Pole. Okay.
Okay, so we know from the direction of the arrows that the air mass is moving like this.
And mine is moving kind of like this.
But what if we took that air mass that's near the pole and kind of pushed it outward towards the equator?
Oh, okay, so like what if this air mass moved from a polar latitude towards an equatorial latitude?
Yeah, in order to demonstrate that, let's draw another air mass that's near the equator.
Okay, so I'll draw mine like here.
Okay, so, and we have our rate equation up here. We know that the Earth spins one time in 24 hours. That's 1 day. So these air masses are spinning around one time in 24 hours.
Right.
However, so their time is the same.
Right.
But the distance is different, because you can see that this air mass has to travel this distance in 24 hours, whereas this air mass has to travel this whole distance.
All the way around. Right.
Exactly.
So their rates are going to be very different.
Exactly. So the distance increases for, say, this outer air mass here, and that means that it's going to be traveling faster than the inner one.
Right. Okay.
Okay. So what if we took this, the one that's close to the pole, and pushed it outward?
Okay.
Well, we know it's traveling slower, and so it's kind of going to fall behind the outer one.
Right, so if this air mass that's near the pole tried to move into the location of this air mass that's near the equator, it's going to move a lot slower when it gets to this place where the air is moving relatively fast.
Exactly.
So in my case, it's going to fall behind as well.
Right. So we've taken an air mass that's near the pole and pushed it outward towards the equator, but what if we do the opposite?
Okay, so what if we took an air mass that's near the equator? This air mass is moving fast, but then, this air mass is moving fast, but over here is moving relatively slow.
Right.
So when it gets out here, it's going to move ahead of any air masses, say they're traveling around the pole.
Exactly, and so this one's going to move ahead of this one as well. So you can see that whenever we move an air mass from in the northern hemisphere here, things are being deflected towards the right. This one is deflected towards the right, and as this one moves inward, it's deflected towards the right.
Oh, okay, so you take the perspective of if you were the traveling air mass, which way do you get deflected? So if I was this air mass, I appear to be deflected to the left in the South Pole, or in the southern hemisphere. But same thing here, if I were this equatorial air mass and I moved towards the pole, I would be deflected to the left again.
Exactly.
So left deflection in the south.
And right deflection in the northern hemisphere.
Okay.